Stars are celestial furnaces, some burning hotter than our wildest imaginations. Supernovas, the death throes of massive stars, unleash even more extreme temperatures. These cosmic events push the boundaries of heat as we know it, but even they pale in comparison to the ultimate heat limit, the Planck temperature. Imagine a temperature so intense that it melts the very fabric of reality. That, my friends, is the realm we're about to explore. Temperature, at its core, is a measure of energy. It tells us how much kinetic energy the particles in a substance have. The hotter something is, the more frantically its atoms jiggle and jive, moving faster and faster as the temperature rises. But what happens when that energy reaches levels so extreme that even atoms themselves are ripped apart? This is where things get truly fascinating. That's the territory of the Planck temperature, a realm where energy is so intense that it warps the very essence of space and time, bending the fabric of reality itself. At this unfathomable heat, our everyday notions of matter simply cease to apply. The rules of physics as we know them break down. The familiar particles that make up our world, electrons, protons, neutrons, dissolve into a chaotic sea of energy, losing their individual identities. Even the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces are thought to unify into a single, all-encompassing force, creating a unique state of existence. It's a picture of the universe in its most primordial and chaotic state, a glimpse into the very beginning of everything we know. To truly grasp the Planck temperature, we need to delve into the bizarre world of quantum mechanics. This is a realm where the rules of classical physics no longer apply, and the behavior of particles becomes unpredictable and strange. This realm of the very small is governed by uncertainty and probability, where the exact position and momentum of particles cannot be known simultaneously. Here, particles can exist in multiple states at once, a phenomenon known as quantum superposition. This means that until we observe them, particles are in a state of limbo, existing in all possible states simultaneously. At the Planck scale, this quantum fuzziness becomes all-encompassing. The very fabric of reality seems to blur, and the distinctions we rely on in the macroscopic world start to fade away. Space itself becomes grainy, with distances smaller than the Planck length, an unimaginably tiny 1.6 times 10 to the power of minus 35 meters, losing all meaning. At this scale, the concept of a smooth, continuous space breaks down. Imagine trying to measure a piece of string shorter than the Planck length. It would be an exercise in futility, as our conventional tools and methods become utterly inadequate. It would be like trying to use a ruler with markings so large that your string simply disappears between them. The very act of measurement becomes meaningless. Similarly, at the Planck temperature, the very concept of temperature, which relies on the smooth continuum of space-time, breaks down. The traditional understanding of heat and energy distribution no longer holds. We enter a realm where our current theories simply cannot provide a complete picture. This is the frontier of physics, where new ideas and revolutionary concepts are needed to understand the true nature of reality. Section 4. Echoes of the Big Bang. So has the universe ever actually reached this ultimate temperature? Scientists believe it did, for a fleeting moment after the Big Bang. In that infinitesimally small fraction of a second, the entire universe was compressed into a singularity, a point of infinite density and temperature. As the universe expanded and cooled, it passed through the Planck epoch, leaving behind only faint echoes of this extreme state. Today, the remnants of this primordial heat can be seen in the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space. By studying this radiation, scientists can piece together clues about the universe's earliest moments, when it danced at the very edge of existence. Section 5. The unreachable horizon. The question then arises, can we, with our human ingenuity, ever hope to recreate the Planck temperature? This is the temperature at which the known laws of physics cease to be useful, and quantum gravitational effects dominate. The answer, at least for now, seems to be a resounding no. Our current technology and understanding are simply not advanced enough to reach such extreme conditions. Even our most powerful particle accelerators, like the Large Hadron Collider, can only reach energies that are a tiny fraction of what's needed. These machines, while incredibly advanced, are still far from achieving the necessary energy levels. The energy required to create a Planck-scale event is so immense that it would likely require a particle accelerator the size of our galaxy. This is a scale of engineering that is currently beyond our wildest dreams, but even if we could somehow overcome this technological hurdle, we would still face the fundamental limitations of physics. The Planck temperature is not just a technological challenge, but a fundamental barrier in our understanding of the universe. The Planck temperature represents a barrier, a point beyond which our current understanding of the universe simply breaks down. At this temperature, the very fabric of space and time is thought to become unstable. What lies beyond this horizon, in that realm of ultimate heat and energy, remains one of the greatest mysteries of modern science. It challenges our theories and pushes the boundaries of what we know about the cosmos.